because GPUs are wonderful. The future is heterogeneous computing. We've been saying that for a decade, and it's now really happening. And the thing is, certain vendors, okay, I pick on NVIDIA almost as much as I pick on Apple, okay? I'm pissed at NVIDIA because they have what's called a walled garden. A walled garden is they've created some wonderful software, and I will tell you, and I will go on record, okay? CUDA and the ecosystem above CUDA is masterful. Okay? NVIDIA realized long ago that they are a software company and have acted that way, and their software shows it. All right? So, bravo, NVIDIA. All right. NVIDIA sucks because all that's closed and locked up by them. All right? And they're doing that because people let them get away with it. Every time you write a piece of code with CUDA, you know, I put this in and I said this in public in front of NVIDIA people at a panel at supercomputing, and it went over very well. If your dog walked into the house and proceeded to do a nice big dump on your carpet, big pile of stinky dog poop, would you walk up to your dog and go, "Oh, good doggy, yeah, that's a good boy"? You know? No, you would discipline your dog, right? You know, it's like, don't do that, all right? All right, every time you write a line of CUDA or a line of OpenACC, you are basically rewarding NVIDIA for crapping on your carpet. All right? And they will quite happily take the money from you. They will quite happily let you lock yourself into their platforms. All right? Don't do it. Don't reward their bad behavior. All right? I know a lot of people at NVIDIA. I know quality when I see it. And it's quality stuff. But if they knew it had to be an open platform, cross-vendor platform, they would spin on a dime. And we would no longer have the stupid situation we have today. Right? If you walk up to me on a CPU and say, "I want to write multi-threaded code," I go, "Okay, you got OpenMP." I don't care if it's, you know, in Intel or AMD or IBM Power or Niagara, or I don't care. You just write your OpenMP code and you're done. Okay? Think about MPI. You walk up, it's a massively parallel machine or a cluster, and it's from who knows who, or you build it yourself. I don't care. You write MPI. Done. All right? A brand new code base at most of these supercomputing centers, you're going to be working these DOE supercomputing centers, these major application code bases you all depend on. They take on the order of a decade to write and refine from scratch to a new code base. When you lock yourself into a single vendor, you are screwing yourself. And so ultimately, I'm pissed at NVIDIA for going down this pathway, but I'm also pissed at the application community for letting them get away with it. Now, I'm going to go on a little bit more about this, but then I'll shut up. One of my heroes is named Mary Zozel. I'm embarrassed to say I don't even know if she's still alive. I'm sure she's retired. But she was, I forget her formal title, but application software coordinator of the ASCII program in the late 90s. And OpenMP exists in part because of Mary Zozel. Because a software company named Cook & Associates and SGI were moaning about the fact that their markets weren't big enough and people were frustrated because everyone spelled parallel do differently. And Mary Zozel said, basically, I'm going to pull the applications community around. I'm going to crack the whip because the ASCII program has a huge impact on funding. And we will only write RFPs for machines that follow the standard you guys are going to lead on. And she stuck to her guns. It's her personality. It's her sense of persuasion. It's persuasion without being forceful. It's persuasion with being supportive. She pulled the supercomputing community around all the DOE labs, not just the weapons labs, but all of them, around this common vision and held them together. And that's what made the vendors realize we can make this work. And that's what led to OpenMP. So OpenMP would not exist without the applications community, and it was Mary Zozel who corralled them and pulled it all together. She is my hero. All right? We haven't had Mary for GPUs. So we got a mess. Do you use CUDA? Do you use SYCL? Do you use OpenMP? Do you use OpenACC? I don't know. So we got to fix this. All right, so I'm trying to fix it this way. We have this SMP model that we've been talking about for OpenMP all day today, but the reality is considerably messier. Okay, there's actually NUMA, and there's things in these slides that talk about how to deal with NUMA. It's content that needs more work, but there is content on that. But there's also GPUs. And this was added in OpenMP 4.0. We kind of finished it in OpenMP 4.5. This isn't new. It's been around a while, and it works. So let me tell you about it. Okay, programming a GPU. To start with, what is a GPU? And I am really embarrassed about the state of GPUs because the jargon is all over the map. How any of you come up to a GPU and don't just barf, I don't understand. Okay? And let me be abundantly clear. I love GPUs. They are wonderful. They are fun. I enjoy writing CUDA code. You know, they're fun. But we don't have a consistent way to talk about it. Okay? So I'm trying to follow Hennessy and Patterson, which is where I pulled this vision from. Because they're an independent third party. They're not tied to any particular vendor's GPU. They looked across them all, and they've tried very, very hard to come up with a consistent jargon. So what you have is a collection of multi-threaded SIMD processors. That's each one of these blocks. So here I've got 16 multi-threaded SIMD processors. Now, an individual SIMD processor, which I blow up right here, has very, very simple processing elements that execute as lanes in a SIMD processor. In an NVIDIA processor, you've got 32 of those lanes. That's why their warp is equal to 32. Okay, so it's like a 32 wide vector unit. So you have a single instruction sequencer that issues those instructions, and all of those guys will do them together. All, well, 32 in the case of an NVIDIA warp. I think in this diagram I've got only 16, right? So you have all these SIMD vector lanes. I'm having a sequence of instructions, potentially a different sequence to each one of these multi-threaded SIMD microprocessors, and they're going to do those instructions all lockstep. Now, let me, before I go any further, this is a simplified idealization. The frustration, not frustration, the exciting thing about the GPU world is it's evolving very, very fast. Okay? If I look at NVIDIA right now, they have tensor processing cores. They have separate floating point cores. They have specialized load store units. All right? So the programming model that I use in CUDA and SYCL and OpenMP thinks of it this way. But remember, there's intense competition on these extra bells and whistles they add, which are explored and exposed through a library API. So you write your code with this model in mind, but you have API functions that take blocks off to a tensor unit or other complex units. But in understanding the basic programming, this is the view. And then you have a memory hierarchy that we put on top of this. So you have private memory at the level of each work item, which is what's running in each SIMD lane. You have local memory, which is shared across all of the SIMD lanes. And then you have global memory at the device level, which is visible to all of the streaming multiprocessors. So this is the canonical model of a GPU. It is an idealization. It is an abstraction. If you look at any GPU, and I mention this because the marketing literature will try to confuse you, right? And they'll throw you and they'll bury you in all those low-level details. But in terms of you as a programmer, this is the model you have. It just has these specialized accelerators that you'll further benefit from. Now, the central idea of GPU programming is the following. Imagine I have a loop. So if I'm writing sequential code or OpenMP code, I think of my code in terms of these iterative control structures which define a loop. So on the left side, I have a traditional loop. I'm doing a multiply, element-wise multiply of A and B to assign to C. What I do on a GPU, and I show the OpenCL kernel code, is I say instead of a single loop, I'm going to create a kernel that just does the loop body. All right? And now what I do is I get my global ID, and I do the loop body for that global ID. Okay, I'm going to say a little bit more just to drive this point home very clear. I take that loop and I map it onto an abstract index space. In this case, it's a one-dimensional index space going from 0 to n minus 1. I define a kernel, which is the code that will execute at each point in that index space. And then I run an instance of that kernel at each point in the index space. That instance is called a work item in OpenCL. It's called a thread by NVIDIA. Pisses me off because now you get into this situation of, oh, and I've heard it in conversations. Well, I got these threads that did this, and then I launched this other function which called a kernel, which had these threads off working on the GPU. And by the time you're done, you're like, what? You're using the word thread for this operating system concept on a CPU, and you're using this word thread. I like your posture right there like this. It's like, oh my God. How am I supposed to keep up on this? Okay, I tried to fix it with OpenCL. Okay, a thread is an execution unit. It is something organized by an operating system to run for you. What you are distributing are tasks among the threads. This is the formal language in OpenMP. On a GPU, what you are distributing are work items. They're blocks of work. Let's not use the same word thread, but I'm sorry, the jargon is what it is, and I wish I could fix that. So what you're basically doing is you're taking your code and you're just writing the scalar code for a given work item. And then you're saying, I'm running an instance of that code at each point in an abstract index space, which can be in OpenCL 1, 2, or 3 dimension. And then I'm going to map those, I'm going to take that index space and I'm going to block it into work groups or thread blocks in CUDA jargon. And then I'm going to schedule them for execution onto the GPU. Now I'm going to say a lot more about that execution model in a minute. And the jargon is bad. All right? So I have the Hennessy and Patterson, I have the CUDA, I have the OpenCL. I didn't even put the Intel jargon on there because it made me sick. I'm sorry, I didn't say that. Because it's the best. and if you saw it, I'd hurt the feelings of the CUDA and the OpenCL people. And I didn't want to do that, no. Yeah, the Intel has its own jargon as well. And I deeply apologize. As a professional language designer working in this space, I feel personally disgusted because I'm partially responsible for this mess, because I helped create all this, all right? And it's a shame. But that's where we're at. I'm apologizing again and again. The fact of the matter is you just have to learn and go back and forth. I wish everyone would just adopt the Hennessy and Patterson and say, look, they're a third party. They don't have a skin in this game. That's not going to happen. Then it's like, okay, what about at least the OpenCL jargon? I don't think that's going to happen either. So you just have to, jargon is contextual, and you have to recognize that things mean one thing when you're talking to NVIDIA people, it means another thing when you're talking to Intel people. Now, let's step back and look at this in more detail. And I'm almost embarrassed to admit how much time I spent on this stupid PowerPoint slide. The area of that red blob is indeed conserved across both pathways. And I know how stupid that is, but I am a purist. Okay, so you got a blob of work. And what I'm trying to talk about here is there is a fundamentally different execution model between the CPU and the GPU. All right? And I love them both. I can't stress that enough. There are times where the CPU is absolutely the right processor to use. There are times when the GPU is the right processor to use. If I'm interested in latency-sensitive workflows, you've got to run on a CPU. If I'm interested in throughput-oriented workloads that are data parallel, you are not going to beat a GPU. So it's not a matter of CPU or GPU, it's a matter of both. And I stress not offloading, not get off the CPU and do everything on the GPU, which is what NVIDIA pushes. What I'm interested in is heterogeneous computing, where you look at your workload and you say, this part runs best in the CPU, this part runs best on the GPU. So having a single programming model that can go back and forth between both is great. That's why I think OpenMP has a real bright future here, but we'll see. So does SYCL. All right, any rate. So you start with the body of work. The program defines work. Now, on a CPU, I break that up into blobs. Okay? On the GPU, I break that up into a larger number, a huge number. It has to be a large number of tiny little blips, tiny little blobs, work items. I organize those work items into units of scheduling called a work group. All right? Now, on the CPU, I map one blob per thread. The threads are concurrent and fairly scheduled and run in parallel across the cores. All right, this is where those words come up. That's why these words are important. On the GPU, they are concurrent, but they're put in a queue on the device. They're put in a queue. And notice, it's kind of hard to see in this color. Oops, I'm sorry. They told me specifically, don't walk in front of the screen. I apologize. Notice I've taken a single work group and put it onto each one of those streaming multiprocessor tiles. Can you see it in the red? I spent so much time. But this is how it works. You define the index space, you define the work items, you define the work groups. All of the work groups for a kernel launch are put into queues, and they're scheduled onto the streaming multiprocessors, one work group at a time. So right now I'm able to run 4 work groups at once. Okay? I can synchronize inside a work group. So the work items in a single work group can synchronize with each other. They can set timing constraints. I cannot synchronize between work groups. All right? That's important. And I'll talk about exceptions in a moment, because there might be some of you squirming in your seat right now, going, well, NVIDIA told me. We'll get to that. Okay? But the core model is I cannot synchronize between work groups, but I can synchronize inside a work group. Now notice, though, that all of the work groups are concurrent. They are available to be scheduled. They are active. But they are not fairly scheduled. And this is why it's very important for you as parallel programmers to understand the difference in concurrency with and without fair scheduling. So CPU gives me fair scheduling, GPU doesn't. All right? Now that's really, really critical, because imagine what happens when you start going multi-GPU. And that's kind of like the cutting edge of extreme scalable systems right now. All right, multi-GPU, multi-CPU. We've done multi-CPU forever. No problem. MPI, done. Two-sided communications, sends, receives, done. Easy. What do you think a send and receive does on a GPU? I do a send, and it's in one work group sitting in a queue, and I do a receive, and it's in a work group running in a streaming multiprocessor, and that receive will never be satisfied, which if there's a feedback loop, that means I deadlock. Two-sided communication on a GPU is really hard. You can do gimmicks to get around it, okay? And people have done gimmicks to get around it. But the point I'm trying to drive into the community, the HPC community today, is the understanding that when you look at multi-GPU, the natural execution model of communication is one-sided communication. Now, I don't know if you've been exposed to one-sided communication before, but you know, I assume because looking at the fact that tomorrow they start with fairly intermediate level and above MPI, I think they're assuming you've all been exposed to MPI. How many of you have never been exposed to MPI? Good, good, because I think that's the assumption coming into this event. That's great, all right? MPI, you have the sends and receives. You have the immediate send to the immediate receive, which is what most of us use. You know, you post all your receives, I receive, then you post your sends, I send when they're ready. And then you have the I wait to wait until they're done. That's MPI 101. What you don't maybe know, some of you probably, but many of you may not know, is MPI also has one-sided communication. So each process opens up a window of memory. And it says, in this window of memory, anyone in the process group can put a block of memory or pull a block of memory, put and get. But you don't have two sides synchronizing and handshaking. It's one-sided, okay? I can say, hey, I'm rank number 1, and I'm going to put this block into the window of rank number 237. And rank number 237 doesn't have to do anything, doesn't have to do a send or a receive, or doesn't have to pair that with anything. So I get this level of asynchrony. And what I do is I decouple the movement of data between these windows. I decouple it from the synchronization. And this gives me a huge amount of flexibility. All right? And what it does is it's the natural communication model on a GPU. So if you talk to the people deep inside NVIDIA, and now because of me, deep inside Intel, we're really big on one-sided communication. We're really big on OpenSHMEM. But I say OpenSHMEM, I like OpenSHMEM, it's another one-sided communication scheme. But for the MPI purists, of which I sometimes call myself, there is one-sided communication in MPI. But one-sided communication gives you a communication model that seamlessly moves between the CPU world and the GPU world. And I submit in extreme scale computing, that's the direction you need to move. So for that reason. All right, so any rate, the generic platform model when you're talking about a GPU is you have a host, which they never say it has to be a CPU, but you know what? It has to be a CPU. You know, the host has to be able to deal with I/O. It has to be able to launch programs across the network. It's basically a CPU. And then you have one or more devices which don't have to be a GPU, but they're basically GPUs. Yeah, they can be tensor processing units, they can be FPGAs, but let's just say for now that there can be one or more GPUs. And they have memory that's only visible to the host and memory that's only visible to the GPUs. It's called device memory versus host memory. And yes, I'm aware they're unified memory models. Okay, so there's for everything I tell you, there's an extension that works around it. But the basic core model you're starting from. And it turns out, even with the unified memory, you're usually better off thinking in terms of host versus device memory. So in OpenMP, I have something called a target directive. And so here's how it works. I've got my host thread running along, and in this case I have two arrays A and B that I declare. And then I have pragma OMP target. And what that says is it's going to take the structured block associated with that target directive, and it's going to move it over to a device and execute on that device. Now, it will by default, in this case, move the data that's fully defined at this point. So it knows that array A, it knows it's a float, it knows it goes from 0 to n. Same for B, and it knows n. So it will copy those items over to the device for you automatically. It'll map those. There's a phrase that's used. And then when you're done, it assumes that you don't need n to move back, but it assumes by default you need A and B to move back. So at the end of the target region, it'll move A and B back. So you need a target directive to get over to the device. And I'm running out of time, so I'm not going to walk through this slowly, but you have it in the slides, because I want to get to this. Once you're to the device, you now want to run in parallel. So, pragma OMP loop. It's that simple. Pragma OMP target followed by pragma OMP loop. Says, move everything to the device. Move the execution to the device. Take the following loop and map the iterations of the loop onto an index space. Take the body of the loop, turn it into a kernel. Take an instance of the kernel and run it at each point in that index space. It's exactly the model I showed you pictures for earlier. Doesn't get much easier than this. This, by the way, is the same trick OpenACC does. Obviously, just like tasks, I introduced you to tasks and gave you enough to get a lot done. I'm doing the same thing here with the GPU. I'm giving you enough to get a lot done. There's subtleties and there's layers of complexity and layers of complexity, all right? You can do an awful lot more. What this construct says very specifically, the loop construct, pragma OMP loop, and I don't need this bracket and that bracket. I can go pragma OMP target, pragma OMP loop, and it'll bind just to the loop. So I don't even need that layer of brackets. So I can put it there, it's correct. So the loop construct is interesting. So Michael Wolff, when he was driving the work on how we map OpenMP onto a GPU, was kind of upset with the fact that the directives in OpenMP are explicit. You don't just tell OpenMP you want to go onto a for loop. You say, and this is the schedule. This is how you will schedule it. And this is how it maps onto threads. Okay? And the threads are there, and they're explicit. You understand they're there, and this is how they interact because they're the team of threads. Everything's explicit. Okay? His position, he was a real visionary on this front, so I like to give credit where credit's due. He was a real visionary that what you want is declarative directives. Directives that say, let me tell you about the problem and you figure it out. Okay, what pragma OMP loop says, and it was added at OpenMP 5.0, pragma OMP loop says the associated loop, the iterations of that loop are fully concurrent. They can execute in any order, and it will not change the semantics of the program. It goes a little further. It says if there's a function in here, that function's not calling anything from OpenMP. So there's no other OpenMP magic going on inside. No synchronizations, no nested stuff, none of that stuff. Okay? It's just simple, concurrent. I can ignore all the other crazy stuff going in the runtime. Just take these iterations and do whatever you want. And it's funny, we had a long drawn-out argument just a few months ago. There's a problem in OpenMP that the spec by design is unreadable by normal human beings, and that is deliberate. How's that? What the language committee in OpenMP will say is the spec is written for the implementer, not the programmer. And that's the trade-off they've made. And what they have right now is I don't even suggest you download and try to read the OpenMP spec. Unless you're a glutton for punishment. I shouldn't say that. Some of you in this room are first and foremost computer scientists. Good for you. And you're the ones who are going to implement the runtimes. You're the ones that are going to work with the compiler people to make things work. You know, we need you people. We depend on you completely. Okay, the spec is written for you. But if you're the physicist or the chemist or the physical chemist like me, it's just, oh my God, no, this is rough. All right? It's why we need people writing books about OpenMP. Like, hey, me, I wrote one. Working on a second. So at any rate, so the loop construct, if you read it in the spec, you have no way of knowing what it actually does. And when I was talking to the spec writers who wrote that part of the spec, they're like, well, it's just the as-if rule. Yeah, that's the as-if rule. So what's your problem? It's very clear. Like, how many of you know the as-if rule? I don't. You know, I've spent my whole career working in computer science. I'm almost a computer scientist myself. As-if rule? Well, apparently, if you're a compiler person, you know the as-if rule. There's even a wiki page for it. The as-if rule says in compiler world that you are allowed any execution as if it cannot be observed as being different from the defined case. So, compiler, you can do anything you want as long as I can't tell it's different than this. That's the as-if rule. And to a compiler writer, that means, including parallelizing it, including creating a loop body as a kernel instance, I'm going to run at each point across the GPU. Yeah, of course. Yeah, anyway, very frustrating. So I finally beat them up on that, though, to make absolutely clear, because I'm writing a book about GPU programming with OpenMP, and I have to make clear that what I say in the book really does map what's in the spec. So that's why I had that fight. But there it is. Now, we have the default data movement I talked about, where if I have pragma OMP target, it moves a fully defined array over at the beginning and back at the end. It turns out you need much more fine-grained control, because data movement's everything. So we have these map clauses. And the map clauses define, am I mapping to the device, am I mapping from the device, or am I mapping to and from? So it's a pretty straightforward concept that I have to be able to control the data movement explicitly. And if I have a pointer, so now I malloc an array, or if it's C++, I use a new, I can pass an array section, because if I just map the bare pointer, what's going to move to the GPU? The value of a pointer to something in host memory. Gee, how useful is that to the GPU? Not at all. But if I pass it an array section, exact same syntax as in the section for reduction, now it's going to move that data over to the GPU. All right? And so I can have map, and if I don't say anything to and from, it's to from by default. Now we are out of time. And in these slides, I walk through some examples of a Jacobi solver. And I show using these constructs, I give performance outlines. And I don't want to go through it now because you've got to be sick of listening to me. And I'm now in your pre-dinner break. And especially if any of you were runners or someone who just has to go out and get your heart beating before dinner, you got to get out of here. I get that. So I want to close. You know, you have all this content, and it's pretty clear and easy to follow, I think. But I want to close with this. Oh, I hope I have it in here. So we have more explicit control. Loop is declarative. We have the explicit control. So I have a target to get from the host to the device. I have a Teams clause, which defines the work item distribution onto the compute units. And then once those come there, I control exactly how the parallelism unfolds through a parallel for SIMD. And then I can distribute the thread blocks by different mechanisms onto the device. So there is the explicit control. It is my hope that you will never use them. Because when you start doing these explicit controls, what you're doing is writing non-portable code. So if you can get away with it, just use the loop and then pressure the implementers to do the right thing as you move platform to platform, then that's performance portable code. And I work very closely with folks, Simon McIntosh Smith, Tom Deacon at Bristol University of Bristol. And we're doing a lot on tracking performance portability. Because if you're going to pressure the vendors into supporting performance portability, you got to be holding a mirror up to them to show them, you know. And I have to tell you, NVIDIA does a great job because their compiler team that implements all this is the same team that implemented OpenACC, is the group that used to be known as PGI. and they are very good. Got that video camera? They are very good. So I talk about these constructs and how they work. It's in there because it's very important, but I want to close with the following. And it's kind of the tragedy of what's wrong here. Because when you look at this, CUDA, OpenCL, SYCL, OpenACC, OpenMP, we're doing the same thing. Granted, CUDA has lots of bells and whistles. Granted, CUDA is like pushing the boundaries on the possible. The problem is it only runs on NVIDIA hardware. But you know, there is, when you start looking at the latest out of NVIDIA, they're doing some magic. They really are. It's great stuff. But look, here's the vector addition problem with CUDA. It's exactly what you write. You know, I have to have the separate function. I have to actually write the function that's the kernel code. That's what's at top there. And then I execute it on the grid, which I define. So explicitly define the kernel function body, and then say, launch it on the grid. The grid is that index space I mentioned. So that's what the CUDA code looks like, which is pretty much exactly what the SYCL code looks like. But now with SYCL, which you'll have a lot more about, SYCL says instead of writing the function, I'm going to do it with the lambda function. So SYCL is tied to C++. And C++ defines the ability to define a function dynamically right in your code. It's called a lambda. And so I have an iterator, and I pass it a lambda for the function. So it's a much cleaner syntax because it's using advanced C++ to express it. So it may look weird if you're not a C++ person, but to a C++ person, this is like, wow, isn't that nice? You know, this is standard C++, no new language syntax. It's really, really elegant. So that's SYCL. But then if I take that same code, this is what it looks like in OpenACC. Same program. So vector addition, pragma ACC instead of pragma OpenMP, parallel loop. There you go. Pretty much exactly what I just told you with OpenMP. Okay? And I can do a more complicated example, and I have it in here. But, and you can see it, but I want to wrap up and just say that, you know, the beauty of it is once you understand that fundamental execution model, you're defining a block of code that we call the kernel. You're having an instance of that code over an index space. Those collection of instances are called CUDA threads or work items, or I don't even know what the SYCL name is. They're supposed to use the OpenCL name. But that's the concept. Each instance of that kernel is at each point in an index space. And it's optimized for throughput, which means I have these blocks that are going to stream through that are concurrent but not fairly scheduled. So it does limit the code I can write. But it's beautiful. And if you do the OpenMP approach, you now have a single programming framework that I can use for my CPU code and my GPU code. And in my dreams, we will someday have the loop construct subsume the target as well. So I can have a pragma OMP loop, and depending on the device is a CPU or the device is a GPU, it'll do everything for you. We're not there yet. But that's where I hope it goes.